Today's talk will be given by Dr. Mingkai Liu, and this is going to be about time-varying metadevices and parametric waves. So if anyone has any questions, you can raise your hand in Zoom, and I will appoint some time for you during the talk to ask a question, or you can write them in the chat and I would ask them myself. Or Mingkai, if you can monitor the participants, also you can choose a time when it's convenient for you to answer the question.
Yeah, so there will be like around 2 sections. So I will probably just have a pause after I finish the first session. So answer some of the question and then go to the next section.
Okay.
So I think, yeah, that will work.
Okay, so great. You're welcome to start.
All right. So thank you very much for the invitation. So hope you are all well during the pandemic in Russia. My name is Mingkai Liu, and I was a former research fellow from the Nonlinear Center, led by Professor Yukisha. So the title of my talk today is time-varying metadevices for parametric waves. So I will have a more like a brief review of what we have done at ANU. And also I will, if time permitted, I will also touch a little bit on some related work on other topics. So this slide is just a brief review of my research topics when I work at ANU. Basically I'm interested in nonlinear and tunable metamaterial and metadevices. And also recently we work on something I would just summarize as what we call extreme performance metasurface. So basically it's metasurface that are, for example, very dispersive, highly dispersive optical material metasurface, or terahertz metasurface that are ultra compact. But today I will focus on I will work on time-varying metadevices because Alexey told me that you're interested in this topic. So I will have 2 sections on this. Basically, it's 2 of our recent work. One is parametric Huygens metadevices, and the other is how to show the potential of using time-varying metadevices for what we call broadband spectral camouflage. So before the talk, I would like to thank my collaborators in these 2 works, including Professor Ilya Shadrov and Dr. David Powell, and Jaya and Alexander from Colin Aerospace, actually. And also I would like to thank our head of department, Professor Yukisha, and all other colleagues for their generous support and very helpful discussion. So I will first, before we go into time-varying device, because this is about time-varying Huygens metadevice, so I'll probably just give a very brief review of what Huygens condition, how Huygens condition is applied in planar devices. So I believe most of you will be very familiar with Huygens metasurface today because it has been a really hot topic over the past, I don't know, 7 years, 8 years. So of course, the basic concept is not complicated. Basically, if we look at textbook from microwave engineering, there's already this concept where it says when you have a boundary, if you can have balanced contribution of electric and magnetic current, then you can sort of tailor the emission, the scattering direction of the wave. And in another term, for a surface, it can be highly transparent. And of course, in most studies, actually, people don't rely on truly magnetic material. So this magnetic part will come from some resonance. And for example, you have resonance that can have an odd parity symmetry. So one of the examples is this magnetic dipole resonance. And of course, I believe today the majority of work actually focus on metasurface. But actually, I would also like to point it out that this concept has also been applied to do similar stuff actually in the ancient time of photonic crystal and metamaterial, but it's just with a different name. Instead of this fancy name called Huygens metasurface, people just call it all-pass transmission filter or impedance match metamaterial. So we already see Huygens metasurface are quite versatile in creating different functionality. And of course, if we want to achieve some advanced functionality for advanced application, for example, radar beam steering or communication or dynamic holography or compressive sensing, and even to create an isolator, right? Then we need to introduce dynamic modulation, and to achieve that, we need a very good tunable metasurface. But of course, there are so many examples already in this field. But if we look at the mechanism behind, basically you can just conclude that they all sort of belong to these two different categories. Right? The first one is to change the material index, so you can either change the environment or to change the material of the resonator. And the second one is just to change the interaction between the meta atoms, such that the response of this couple meta molecule, for example, will change accordingly. So of course, you might think tunable metasurface or tunable metamaterial is very straightforward. You just add something tunable in there and the resonance will shift. But actually, if we look at this problem in a more in-depth manner, and if we ask a question, and that is what makes a device ideal? So what is an ideal tunable device? So, and our answer is actually, if we look at the electromagnetic wave, we have many degrees of freedom. For example, the amplitude, the phase, the polarization, orbital angular momentum, etc., etc. So ideally, we actually want the device can tune these different degrees of freedom, not only independently, but also arbitrarily. For example, we want to have a device that can change the amplitude from 0 to 1 without affecting the phase, or to change the phase from 0 to 2 pi without affecting the amplitude. And also we can do the same thing for polarization, for direction. But the reality is it's very difficult to realize such independent and arbitrary tuning. The reason is because these multiple degrees of freedom are actually, I would say not, it's very hard to independently tune them. And so this is just like, you know, the reality, right, versus the real expectation. The physics behind such challenge is actually something related to the fundamental Kramers-Kronig relation of the response function. So if you look at the basic idea of existing tunable mechanism, basically is either change the resonant frequency or to change the line width. But doing so actually will shift the whole response function globally. And from Kramers-Kronig relation, we know that once you change, for example, the real part, the imaginary part will also change accordingly, because they are related in a global manner. And the same apply to the amplitude and phase. So when you change the amplitude, you have to change the phase in general. Now, in the microwave community, actually, people have already tried to solve this problem by bringing by utilizing actually Huygens metasurface. So actually, people propose that in order to achieve, for example, pure phase tuning in transmission, then you have to independently tune the electric and magnetic response of the metasurface. But it turns out that this is far more challenging, because when you have loss, then the situation becomes very complicated. Basically, you have to not only control the electric and magnetic response, but also the gain and loss, because the electric and magnetic resonance have different sensitivity to gain and loss. So it's very difficult still to manage such independent control of the different degrees of freedom in the response. So back to 2015, we kind of think, okay, if this linear tunable mechanism is so difficult to achieve, we can probably use another mechanism, and we think about this time-varying modulation, which was also started to become a hot topic in metasurface. So there are two very important features in this parametric process based on time-varying modulation. The first one is it is a linear process. So the frequency, sorry, the power generated in the sideband actually is just linear proportional to the incident power, and so it's not like a harmonic generation. But of course, you can also say generate new frequencies. So in this sense, it's nonlinear. And the second one is it's a non-reciprocal process. So people already try to use this process to achieve time reversal symmetry breaking and realizing isolator or circulator. And I think the most interesting aspect of this process is that the phases of the sideband actually have gauge freedom. So essentially, if you look at the response of, for example, this very simple modulation function, you can sort of expand it in the Fourier series. And if you look at the phase of each Fourier series, that will correspond to the sideband, you can see that actually this phase is related to the modulation, external modulation phase. So that means now we can actually control the phase of sideband using the external modulation phase and not restricted by the initial linear resonant response of the system. So the basic idea of using this approach to realize an arbitrary tunable meta device is that instead of relying on the linear response, we try to convert the incident frequency efficiently to another frequency, to one or more new frequencies, and then control their phases via dynamic modulation. And the reason we want to bring time-varying modulation and Huygens meta device together is because we already see there's a lot of advantage using this Huygens approach. So we want to leverage some of the advantage in Huygens metasurface to bring in this advantage to the parametric wave control. So of course, this is not something we came up with in the first, we're not the first one to come up with this idea. Actually, parametric process is has a long history. For example, in microwave, in acoustic, in photonics. Right? So here I just choose some of the early work related to time-varying arrays, because we are talking about metasurface, so I think the most related one is time-varying array. And these work primarily focus on realizing non-reciprocal effect. And so we come up with this time-varying Huygens metasurface idea back to 2015 probably, and then it took us like 2 years to realize the first device, this device, and submit a paper. And then after that, we already see a huge explosion in the number of paper in this field. And actually, apart from the field in metasurface, actually people working in antenna community already have worked on similar topic, but they just call it like, I don't remember the exact name, but probably time switch antenna array or something like that. So, and also recently we see the development in this field that people start to work to realize this concept in terahertz, from microwave to terahertz, and then to infrared, and then to optics. And also the design of the metasurface become more and more mature actually. So this is the again the basic concept. So we want to convert the carrier wave very efficiently to the desired sideband, and then by controlling independently controlling the modulation of the electric and magnetic current, we are able to achieve different functionalities for different parametric waves. So as you can expect, the process of bringing time-varying modulation to Huygens metadevices can be quite complicated, because each meta unit, let's say, each Huygens unit have one electric and one magnetic atom, and then they are already independently modulated in time, and also these elements are all coupled in the array. So, so in order to describe this process, we sort of developed a theoretical framework by combining the generalized sheet transition boundary condition and the the effective impedance model that describe the nonlinear and linear interaction of this meta item. So the first question we want to answer with this model is whether this complicated interaction will affect the gauge freedom of the sideband. And after some analysis, the answer is no, it won't. And that's something relief, because at the beginning we are not actually quite sure whether this complicated interaction will affect the gauge freedom actually. And the second one is why we want to combine the electric and magnetic response. And it turns out that from the theory analysis, it shows that in order to achieve high conversion efficiency, actually it is necessary to bring in electric and magnetic response. And also another advantage, as I will show later, is that because now the electric and magnetic scatterer, right, will have opposite parity in their scattered field, and not because they have a gauge freedom that can be controlled just by the external modulation phase. So that means now we can basically have a full control of the directionality of the sideband using a different modulation phase difference between the electric and the magnetic resonator. And also from the theory, we can actually very easily retrieve what is the required time-varying modulation in the transmission and reflection for a particular type of sideband generation and sideband scattering. For example, here in the column A, you can actually see this single sideband forward, say forward directional scattering. And in order to achieve, like for example, in the ideal case, a very perfect conversion from the carrier frequency to the minus first order sideband, and then we want this sideband to scatter forward in the forward direction. Then what we need is actually to have pure phase transmission modulation, where you can have the phase vary linearly, right? But meanwhile, you need to minimize the reflection as much as possible. And in another example, for example, for this double sideband bidirectional scattering, then you also need to have pure phase modulation, but then you have to modulate both the reflection and the transmission, and the reflection and transmission are modulated in a conjugate manner. So in order to realize this concept, we just bring up with what people already know, or how to generate electric and magnetic resonator. So we just combine the electric split ring and the magnetic split ring resonator, and use varactor diode as the tunable element. And this figure actually shows the voltage dependent amplitude and phase response of the transmission and reflection. And here in our design, we specifically designed the structure such that at the Trojan frequency, we can achieve 2-pi phase change in both transmission and reflection. So if we sort of judiciously choose the bias voltage of the electromagnetic atom, then in principle we should be able to achieve the desired phase and amplitude at the transmission and reflection. So based on this structure, we did some simulation, and we found that actually indeed if we choose the modulation voltage correctly, then we should be able to achieve a reasonably high conversion efficiency from the carrier wave to the sideband. So for example, in this column A, we showed the sideband efficiency for what we want is this forward single sideband scattering. And this is the column B is this double sideband forward scattering, and column C is the bidirectional scattering. Now, if we compare what we actually achieve using this realistic design and the one based on this boundary condition, of course, there is the actual result is, of course, there will be some difference because the structure is not perfect. In particular, in the amplitude, because there is absorption, so it's very difficult to stay a constant value in the amplitude. But if you look at the phase, pretty much we are approaching the ideal situation, and actually the phase play a significant role in achieving what kind of sideband scattering we want. So we also did an experiment. We just fabricate a single unit and put it in a rectangular waveguide to measure the response. And this is just the diagram of how the experimental setup looks like. And in order to optimize the modulation waveform, we actually use genetic algorithms. So we sort of measure the scattering spectrum and then optimize the modulation waveform in an interactive manner.
Sorry, Mingkai, there was a question from Constantin about if when you calculated the efficiency, you took the losses in the varactor into the account.
Yeah, no, sorry. Yes, I didn't mention. So here is the pure power from the scattering, and because the varactor diode will have loss, so this loss is not taken into account, and the loss could be quite lossy. Later we found out it could take up to 60 to 70% of the energy. So here the efficiency is normalized to just the scatter power. Yes. So so here is the experimental result. So you can see if we optimize the modulation waveform carefully, then we should be able to achieve reasonably good conversion efficiency. And in fact, if you compare the modulation waveform and the theoretical one, you can see actually they're pretty close. Okay, should I answer some question or?
No, there is no more questions at the moment.
Okay. So so one of the very interesting, as I mentioned before, is we can now actually control the directionality of the sideband scattering arbitrarily. So in order to show that, we sort of choose to just fix the optimized waveform, right? And then we simply change their relative phase difference between the electric and magnetic modulation. So effectively, it's like a different time delay between the modulation waveform. And by doing that, we can now clearly see we can change the directionality from say sort of perfect forward scattering to a perfect backward scattering in a continuous manner. And the most important thing is we don't change the overall power efficiency. So this is not something that can be easily achievable using linear metasurface, linear tunable, conventional linear tunable metasurface. And of course, when we submit the paper, our referee said, it's good, but still not convinced. So basically, we have to go back and then try to come up with a solution that based on a finite array. And so basically here we just redesign or re-optimize the structure such that the electric and magnetic meta-atom now can be printed on the same side, on the opposite side of the substrate, and they can be packed in parallel plate waveguide for measurement. Now, if we look at the transmission and reflection, the voltage, bias voltage dependent transmission and reflection coefficient, we will see actually it's very similar to the one we achieved with a single unit in a rectangular waveguide. So we'll expect that this design can also work in a similar fashion. And so this is the final sample. So we have made a finite array. So it's not a very long array. It's only like 2 lambda, so 2 working wavelengths in length. And it has 16 units, but because we have a lot of lump element. So basically we have to, I have to sort of solder all the soldering point, and we also need to bring a long enamel wires for all the control unit. So, but anyway, so this is the experimental measurement setup. So we launch sort of a plan wave using this parabolic mirror, a plan wave, and then launch to the time-varying metasurface, and then this wire just transmit the modulation voltage to the metasurface, and then we use the near field measurement. Use this near field 2D scanner to measure the field distribution.
I think there is another question about from Stanislav on how the bias voltage was applied when a single element was placed in a waveguide.
So we simply just connect the enamel wire through the gap of the 2 sections of the waveguide. Yeah, so because the enamel wire is sort of insulated, so it won't affect the, it won't be shorted by the waveguide section. Not sure whether that answers the question, but yes, the control, the voltage is supported by the arbitrary function generator, which is connected to the computer, and then the waveform is also controlled by a MATLAB code, and then use the genetic algorithm to optimize. So here is the field we measure for different sidebands. So basically now what we show here is what we call frequency multiplex functionality. So you can see for different sideband, we can actually have, for example, different steering direction, and also to have different device functionality. For example, for this one, you can have a focusing performance for one of the sideband, and then have defocusing performance for the other one. Another interesting effect is now you can also steer the sideband 360 degree around the metasurface, and because now we can sort of control the relative phase between the electric and magnetic atom, and also the phase pattern along the metasurface. So now we can have a full control of the direction. And I don't think this is something that is easily doable with a single metasurface. I mean, with a single linear tunable metasurface, I don't think it's a very easy task to do actually. But with time-varying metasurface, it's relatively straightforward. So I would just sort of conclude the first section. So if you have any question, please feel free to ask, and I will just have a sip of water.
Okay, Alexey has a question, I think.
Yes, so...
Yeah, Mingkai, very simple question. I try to understand the setup of your experiment, how you did the measurements. I thought that it should be in the reflection scheme, but you have shown that you do it in the transmission and measure the field. Can you go back to slide number 27? I believe there you have shown the setup.
So the near field measurement, right?
Yep.
Okay.
Yeah, probably previous one, or yes, this one. So it seems like you have excitation from one side of metasurface and measurements from another side of the metasurface. So how it was realized generally?
So the source here is simply like a monopole antenna, right? So
okay.
just excite the point source, and then use this parabolic mirror to launch a plane wave. When it hit the metasurface, so you can have on the top plate of the parallel plate waveguide, you can scan the field. So it's not necessarily the transmission, but you can also measure reflection as well. So that's why we can measure the full 360 degree profile. But speaking of that, actually, this parabolic mirror also cause some problem if we want to access the true reflection of the carrier wave, and that's something we can't do because it's sort of mixing with the incident wave. Yes. So, but for sideband, it's reasonably well, I would say. Somehow the mirror doesn't bring huge perturbation to the final result. So.
But this 2 lambda sample is kind of more or less enough to approximate like infinite metasurface, yes? If we will, let's say, increase it like 2 times, do the efficiency or whatever will improve dramatically, or it would be like 1% or something like this?
I would say for sideband conversion, it probably doesn't make much difference. The only difference is when you have larger array, you have probably better directivity.
Mm-hmm.
It's just like an antenna array. So yes.
Mm-hmm. Thank you.
I don't see any more raised hands. I have had a question myself on if this can be achieved or implemented in the near field, because as far as I understand, you're working now in the far field.
What does it mean in the near field?
Like when you have say less than one wavelength from the source to the metasurface. So does it work only with plane waves, or
You mean the parametric process, or what kind of
the incoming
functionality?
well, I mean,
I think I think in general, the parametric process should work. Whatever kind of excitation, whether it's far field or near field. The only difference is probably when you come to near field excitation, then you probably need some specific tailoring of the phase profile. It's because for plane wave excitation, it's relatively straightforward. We just need to consider what kind of phase we need for the scattering output. But if we have near field excitation, then we have to compensate that as well. So and also you also probably will face the difficulty that if the excitation angle become very large, then your coupling coefficient will be probably will be lower in this case. So, but I mean, if you look at this example of focusing, I think the focus of the wave actually is probably around 1 lambda to the surface. So yeah, in this sense, it should be more reasonable.
And then is there any limit on how different the omega 0 and the capital omega should be, or they can be like arbitrary?
Well, here we only work in the regime where the modulation frequency is much lower than the carrier frequency. Mm-hmm. Of course, if we go to the situation where your modulation is comparable or to even larger than the carrier frequency, then the situation can be quite different already. To be honest, I haven't really studied what will happen in this regime. But people working in, for example, like conventional mixer actually is this kind of situation. But in those situations is like the process is like happen on chip, right? So, but for free space scattering, I think this is still something need to further explore. So, and also if the modulation frequency is very high, then probably you also hit the say the response bandwidth of your like the RLC bandwidth of your bias network, and because it's essentially it's sort of a low pass filter, I think, for the bias network. So if the frequency is too high, it just doesn't go through. So
okay, thank you.
Yeah.
So at the moment, I don't see any more questions.
Okay.
I think there is a question from Varvara, right?
Yeah. Thank you for a nice talk. Can you show again the azimuthal dependence of the meta device?
This one, right? Is it?
Yeah, this one and the next also. Yeah. So it's look like the scattered power of the So what is the different color is only for different scatter angle, yes?
Yeah, for different, based on different phase pattern.
Or this is for shifted frequency. So is the scattered light is has a equal amplitude? So
No. It's a very common problem for array antenna actually, and no matter it's parametric or linear. So when you come to large oblique angle, then the efficiency will become, in general, will become weaker, right? And that is the reason behind is because the impedance for different angle actually are quite different. So here we only change the modulation phase in order to just steer the beam, right? But in order to optimize the efficiency for each angle, actually we probably also need to optimize the modulation waveform, for example, modulation amplitude, and all sorts of these things. But in general, yes, it's a problem, a common problem in array system where you get degraded performance at large angle. So I'm not sure whether I answered your question.
It's okay. And I have a little question more. So what can you say the number of capital omega and the fundamental omega? So what is the
this one, I think the carrier frequency is 4 gigahertz for this array. And the modulation frequency, I think, is, I don't remember, it's probably 2 megahertz, I remember. So, yes.
Okay, thank you.
Yeah.
Okay, thank you, Mingkai. I think we can move on to the next part of it.
Yes. Okay. So the second part will be some more like science fiction application of time-varying metasurface. So what we call broadband spectral camouflage. So it's related to Steele's technology. And so before we go to the metasurface part, so we just have a brief review of how the radar works. So basically for radar, we launch the signal to the target we want to detect. And then we will probably see a frequency shift in the detected spectrum. And that is correspond to the Doppler or microDoppler shift, which will provide the information of the target's dynamic. For example, the speed, the rotation, etc., etc. And also, if we combine the information of time of flight, then we will be able to get the range information. And one of the example, and now if we look at this problem in the coordinate of spectrum and momentum, so basically the Doppler shift will just contribute to a frequency shift, and the scattering will contribute to a spread in the momentum. And so one of the example is the commonly used radar, what is called frequency modulated CW radar for automotive vehicle. Actually, all these driverless cars rely on this type of radar. So instead of using CW radar or short pulse radar, so they actually choose frequency chirp radar. So within each cycle, the frequency is modulated linearly or in using other different waveform. And then the detected signal, right, reflected from other cars will provide you the information of the Doppler shift, which can tell you how fast the relative speed between your car and other cars. And also the time of flight information will tell you the distance between your car and other cars. Now, I believe this is just one of the example, and I'm definitely not the expert in radar. So, but this is just one of the example to show how radar works. As the community of metamaterial and metasurface, we have this glorious history of making things invisible. So probably start back to 2016, right, when this very famous paper by Sir John Pendry actually show how we can make an invisible cloak using transformation optics and combine with metamaterial. Now, of course, in practice, although the cloaking concept is quite fantastic, but in practice, probably it's more commonly to see radar absorber and radar diffuser. And for absorber, it just simply means it absorbs the energy and reduce the scattering cross-section. And for diffuser, it actually will try to avoid too much absorption. Because I heard that there are some very powerful radar from the Russian army that can actually cook an egg 5 kilometers away. So I believe if that's the situation, it's probably better not to absorb too much radar power. So instead, for this diffuser, just people try to use this diffuser to spread the wave to a wide range of angle in order to reduce the power density at the direction of the radar. Of course, there are so many examples in using different technology, including metamaterial and metasurface, to realize this concept. I'm not going to go through all these examples, but what I would like to do is just to look at this problem from in the coordinate of frequency and momentum. And so basically for cloaking, if you look at what they actually do is they actually try to minimize the momentum change of the scatter wave as little as possible. And of course, things are always not perfect, so you always have some very small amount of backscatter power, and that will be detected. Now for absorber, it's the different story. Instead of trying to perturb as little as possible, the momentum actually in absorber we try to convert the propagating component to evanescent component, and then to shift this momentum to the outside of the light cone, so to change this propagating wave into fast decaying evanescent wave. And for diffuser, in contrary, is we try to avoid too much absorption, so we just want to spread that momentum within the light cone. Now, of course, you see this coordinate of frequency and momentum. So you probably will ask, how about, or if there's anything we can do to achieve similar effect if we manipulate things in the frequency domain instead of the momentum domain. So, well, oh, sorry. So, and that is exactly what nature has been doing. Nature rarely actually manipulate light in the momentum domain, but they actually they are master in manipulating the color. For example, in this example, you can see this chameleon actually change its color quite rapidly according to the environment. And this one is actually a moth, which actually resemble the branch very nicely. So correspondingly, if we compare these two examples, and we can probably come up with something similar for radar. And the first one, which is based on the shift of the change of the color, is what we can call a Doppler illusion. So basically, instead of backscatter the true Doppler feature that will reveal your true speed and acceleration, you can manipulate the reflected Doppler feature, and such that you probably, even your hypersonic flight, hypersonic jet, you probably will look like a bird or even stay still, right? And in order, and the second example is what we call spectral camouflage. So instead of converting this very sharp Doppler feature to another frequency, we sort of convert this sharp feature into a very broad band, like a white noise, and just like the environmental background noise. So these two, I will say, instead of making things invisible, it's sort of a deceptive way to hide from radar. And what we can achieve, what sort of platform we can achieve this functionality, I believe you already know it's based on time-varying metasurface. And the example I showed before is sort of already, if you consider the single sideband conversion, it's sort of already a Doppler illusion, because effectively it changed the frequency of the wave passing through the metasurface. So now I will just focus on another one, is called spectral camouflage. Now, when I come up with this idea, I was quite excited because I said, there's a new way to, making things invisible. But it turns out that actually this idea has been come up by Professor Tannen from UK, actually more than 20 years ago, when I was still a primary school student. So so if things that the idea is too good, then probably you, in particular for us working in electromagnetics, we will probably really need to go back to read the literature published many years ago. So the basic concept is actually quite similar to what we come up with, is that if we have a screen, a reflecting screen, now if we can switch the conductivity and such that the screen will behave as a perfect electric conductor and a perfect magnetic conductor, which effectively will bring a pi phase shift and a 0 phase shift in reflection. Now, if we do this modulation, this switching, alternatively in time, then of course the energy of the scatter wave will be converted to some new frequency. And if we look at the say the average reflection power at a carrier frequency, we will actually see that it can be suppressed quite significantly. And of course, people still sort of treat it as an active radar absorber back then. But you can see that actually if we manage the modulation sequence well, actually we can achieve a pretty good reflection suppression at a particular frequency. So of course, most of the work in this actually are quite dispersive, quite narrowband, and they're polarization dependent, and also highly sensitive to the incident angle. So what we try to do is to extend the frequency range, and because you never know what the frequency of the radar will be. So instead of working at a particular frequency, it's better to work over a broadband. And to do that, we just tailor the meta atom such that now it can support two resonant mode. And one is look like a dipole resonance. The other is like a toroidal one. So now if we switch the ping diode, then we should be able to see a pretty significant phase shift in the reflection over a broadband. And we have to tailor the geometry such that this broadband, this phase difference remain almost constant over a broadband. So this is the phase difference between the on state and off state. And you can see that actually it can stay around pi over a reasonably broadband. Now, if we are only interested in the reflection power level of the carrier wave, then we can just calculate this with this very simple formula. And this D here is just the duty cycle of the when the matter surface is in the on state, right? And so basically it's just the summation of the reflection coefficient of the on state and off state. And because they are now anti-phase, one is 0, one is pi, so they will just add up together and will approach 0. And from this, you can see, indeed, if we change the duty cycle from 0 to 50%, then we should be able to tune the effective reflection from 0 dB to below minus 10 dB over reasonably broadband. Now, the interesting thing is the design I have is for normal incidence, but then we shift to, we look at what will happen at oblique incidence. And immediately when we go to oblique incidence, we see some very sharp resonance. And this resonance, we believe, is something related to leaky waveguide mode, or in today's fancy term, is also related to I think bound state in the continuum, which people already see in the photonic crystal. And also, but nevertheless, what we try to do is here is to re-engineer the bias network, and we need to add some additional loss to the bias network such that it suppresses the high Q resonance, but keeping this broad resonance on the top matter surface intact. And so this is the result of the, after we optimize the design. And so we actually, now we can maintain this broadband feature over a wide range of incident angle for both TE and TM polarization. So now what we have shown here is for the carrier wave. Now we look at how the sideband will look like. Now, so here is a numerical experiment. So we just launch a radar pulse, like have a 15 microsecond long radar pulse, which consists 6 CW carrier frequency. All right, so you can see the frequency from the reflection spectrum. And this is just the reflection spectrum when the metasurface, when our design metasurface is static. So basically, it just looks like a high reflecting surface, so nothing special. And now if we introduce periodic modulation, so we now switch between the on-state and off-state periodically. And if we look at the spectrum of the reflection, immediately we see a lot of frequency comb generated. And actually, the level of the frequency comb is actually, the power level is still pretty high. And so that is not something we want in the, for radar detection. We don't want to show this high power sideband. So instead, now if we introduce some quasi-random modulation, so now our modulation will become sort of a broadband white noise-like spectrum. And if we look at the sideband, right, then we will also see such feature. And effectively, we will see the incident power now is largely converted to this broadband white noise-like spectrum. So as a rule of thumb, so you might ask how much we can reduce the sideband power. So as a rule of thumb, based on power conservation or energy conservation, then we will expect that the level of sideband is proportional to the ratio of the incident signal, the ratio of the bandwidth of the incident signal and the bandwidth of modulation. So in other words, if we have a long pulse and a fast modulation, then we should be expect to see a larger suppression in the sideband power. So you may notice that these two frequency doesn't get suppressed, and the reason is because these two frequency are outside the working bandwidth. And I here just to add these two frequency to specifically show how much we can suppress the power level. So so far we focus on say homogeneous modulation of the whole metasurface. Right? Now, if we want to further reduce the power level, then we probably need to combine space and time varying modulation. So here is just the momentum distribution of the scatter wave of the carrier frequency and the sideband, and when we only have time varying modulation. Now this one, in comparison, is when we have space varying modulation. That means we have a pattern, for example, with a reflection phase. One is 0, the other is pi. So we have this random space modulation pattern. And if you look at the power level, so we can actually reduce to around minus 23 dB. Now, the interesting thing happen is if we combine these two, and we do a space-time varying modulation. So first we see a further decrease in the carrier frequency, the further reduction of the power level at the carrier frequency. And at the sideband, we see a very drastic decrease. So basically, because at sideband, as I mentioned before, there is gauge freedom in the phase. So this space varying pattern now actually can also be imprinted for the sideband modulation. So as a result, we see a very drastic reduction up to like below minus 50 dB. So, so why this is interesting actually for spectral camouflage, if you consider this process as an encryption of the radar signal, in a way, it's like your metasurface now can control who can see such radar signal, right? So, of course, for example, in a battle, you always want to hide from your enemy, but you want to be visible to your own party. And that is why if we have this random modulation coding apply on the metasurface, and we sort of encode the radar signal. And our enemy, of course, if he doesn't have the correct modulation sequence, it's very difficult for them to retrieve the correct Doppler feature. But if we provide the correct sequence, the modulation sequence to our own party, then there's no problem for us to detect our own flight or target. Right? And another thing we later noticed is actually this spectral camouflage is closely related to in the communication is a technology, actually is the physical foundation of what they call spectrum communication. If you are not familiar with this term, you are probably familiar with CDMA. So actually CDMA is one of the standard in 3G communication. Now, although now it is already abandoned in 5G, but it is still widely applied for military. So you can see actually from this example that time varying metasurface has many potential in application related to other areas. So I think I would just conclude this section here. If you have any question, feel free to ask. Am I run out of time already?
I think we have actually some time for questions, if there are any. While there are none, I'll ask mine. You mentioned that when you showed the decrease of reflection for the sidebands, it looks
Yes.
like there is a sort of discrete amount of sidebands in which are
Yes, so that is for periodic modulation. So if we have periodic modulation, then definitely it's a discrete amount. It's just a discrete Fourier transformation.
So for quasi-random modulation, it's not.
Then it should be quasi-continuum. I would say not complete continuum.
I mean,
it's quasi-continuum.
It looks kind of. It looks kind of sort of useless against the chirp-pulse because that one has a frequency sweep, and thus it would sort of fall into the gaps between the sidebands. Or is it also?
You mean?
You told in the beginning that the radars are often chirp-pulse based, where you have.
Yes. So I think it is still useful because effectively you are just shifting the carrier frequency, but because within this working frequency band, right? So you always come up with noise, sort of noise. So it's impossible for you to see any a true Doppler feature. So yeah, it is still impossible to find out what is the real speed. I'm not sure whether that makes sense.
Yeah, looks like it should work. And another thing is when you're mentioning the radar encoding, is there any way to say to counteract the time of flight? Because depending on the time of flight to the target, it looks like you would have different modulation function and sort of demodulation function. Depending, because you sort of somehow need to synchronize the modulation function on the target.
Yes, you need that. Yes.
And the receiver. And if you don't know the distance between them, it's sort of. Do you think is that there?
Yes. So, but I think you probably need a little bit cycle to figure out the distance and how it changed, and then you sort of adjust that accordingly, probably. But only say I'm not an expert in radar detection, but I believe this is something that can be solved because, for example, in as I mentioned, for this spectrum communication, it's already widely applied, and basically in communication, apart from using, as far as I know, apart from using this quasi-random modulation, people also use some sort of like an address coding to distinguish different user, right? So in that sense, apparently it will be possible to figure out where the user is. So yeah, so I think it's something for radar expert. It shouldn't be a big issue. So yeah.
Okay. So I don't see any raised hands anymore. There is also a question again from Varvara that says, are you reading the question?
No, I can't see the question.
Yeah, so it says that you said there are two modes, electric and toroidal. Is this thus the anapole mode?
I won't. I'm not sure actually because Let me go back to this slide. Here, right?
Right.
Yeah. So I don't really see the. Well, I mean, it's sort of course, you can always find some frequency in the middle that you have such interference, but at that point, but it's again, it's a reflection type. So when I say dipole-like and toroidal-like, it's simply based on this planar surface current. So it's probably very different from, a little bit different from what people have done using studying this all dielectric anapole toroidal stuff. So
yeah, okay, I guess that sort of answers the question. So no more, I don't see any other questions. So thank you, Mingkai. That was
yeah, thank you very much.
very interesting.